Welcome to Systems SYS1 Week 2 review, what you should know at the end of the week. As always, the key things are the labs and the exercise sheets, so make sure you have done those. For the lab, we were looking at hardwired controllers. So to put that into context, as chatted on the tech review session, there's two fundamental design philosophies when it comes to processor internal control. So you can either go hardwired or microprogrammed. So you typically see hardwired controllers in RISC type architectures like we'll be building in the simple CPU. So with the RISC philosophy, so a reduced instruction set computer, we try to minimize the hardware. So the general design principle is that if you have less hardware, you can clock it faster and therefore you can process more instructions per second. But those will be simple instructions, so reduced simple instructions. The alternative philosophy is a CISC architecture, so a complex instruction set computer. And there we would typically use a microprogram controller because the instructions we'll be processing are more powerful, they're more complex, so therefore they'll need more control signals and it would be tricky to design as a hardwired controller. If you'd like to look at a CISC microprogram controller, you'll find an example on my webpage. If you go and look at the simple CPU version 2, it's based on a microprogram controller. We won't be covering this in this module, but we will come back to microinstructions in a later lab when we simulate the simple CPU in CPU Sim. So we could dive straight in there and design our hardwired controller for our processor, but to allow you to take a smaller step, we're going to design a bug controller. So what you have is our trap. It's got 4 inputs, the 2 sensors and the 2 switches, and 2 outputs, the servo and the LED. So we're going to design a controller to process those inputs to control those 2 outputs. So we chatted about the basic architecture. So we saw here, we started to introduce the ideas of parallel buses and serial buses. So from your point of view, the bug trap controller uses a parallel bus. So you have a 4-bit bus. A bus is just a collection of wires. So the 4 signals carrying our 2 sensors and our 2 switch data into our schematic that we'll be using. And that was actually abstracted away using our virtual wires to a serial bus. So the I2C protocol. And if you'd like a little bit more information on that one, you'll find a PDF on the VLE. Okay. So we had our first controller, and yeah, again, just to re-emphasize, active low, active high signals. Do make sure you're happy with that one. So the bug trap switches and sensors were active low or negative logic, so they were active with a logical 0, whereas the servo and the LED were positive logic, so active on a logical 1. And as discussed in the technical session, there's good electrical reasons why we do use active low signals. Okay, we move forward. So make sure you're happy with the hexadecimal representation, so that 4-bit value coming in being displayed as a hex digit. Make sure you can work out what signal is connected to what bit, as described by this table here. So then we moved on to the main design element of this lab. So we're converting the high-level descriptions that describe our bug trap behavior into our circuit diagrams, into our AND gates and OR gates. And the first one we saw was a simple NOT gate described with these rules here. The thing to remember is obviously when we design a processor in later lectures, we'll be doing the same thing. So we'll take a high-level description of what the processor should do, and that will be typically described as an RTL syntax. So each instruction, you'll have a register transfer level, an RTL description of what it should do. You then need to convert that into the sequence of control signals generated by your hardwired controller to control all the architectural units inside our processor. So the ALU, the registers, internal data storage, or the external data storage, our memory. So the lab progressed and we increased the complexity of our bug trap, adding more and more behaviors. So this is kind of one with automatic and manual modes engaged. We saw that actually internally there was multiplexers involved, so we could implement it actually from a multiplexer, as you see in our final implementation. And you had to fill in the blanks to actually get that to behave. The key thing I just want to really emphasize is make sure you could do that, make sure you could draw that schematic and you could simulate it and you got this simulation diagram. So yes, a checkpoint here. So do make sure you got this simulation diagram. If you didn't, give me a shout, we can chat, but this is where you should have got up to in the lab. Okay, the second important bit is the exercise sheet. So do make sure you're happy what a multiplexer is, how it operates. So a little bit of a nonsense circuit here, but we can use multiplexers to implement different logical functions. So when you look at this circuit diagram, this multiplexer wired up, obviously it has 4 inputs controlled by 2 bits here. So from a black box point of view, you've got 2 inputs, 1 output. So each one of these circuits implements a 2-input logic gate, and make sure you're happy what those are. Again, one of the key things of this module is we want to take these building blocks and make more complex components. So it's not just understanding how, in this case here, a full adder works, but how can I use that to do something useful inside the processor? So how can I make an incrementer? And we'll obviously be doing that with our program counter when we get into looking at our simple CPU. So to start you down this road, can you take this full adder component and combine it with another one to make a binary incrementer? That is a component that will take a 2-bit value in. So here's our 2-bit input value. So input value x, so it's 2 bits. So I'll have x0 and x1 are the 2 bits representing my input value. And obviously we want to make a circuit that will produce an output value, again another 2-bit value, which will be one value higher. So if I input a 0, I'll output 1. If I input 1, output 2, input 2, output 3, input 3, output 0, 0. And why is that, as it says there? Why can't I represent the value 4? Following on, we continue the development of our bug trap. And again, this is focused on effectively building another decoder. So what we will have is a command code coming in, so a 3-bit command code specifying the movement of our robot now. So rather than specifying how we should control those H bridges, now we want to have another command code which defines the robot's movement, not the individual motor's movement. So we have to convert that 3-bit code into the 2-bit codes which will be used to drive the 2 motor controller blocks that we designed in the previous exercise. So these are the motor controller logic blocks you designed in exercise 1, being controlled now by another component. So when I enter the command code 1, that's the command code for forwards, and obviously I want both motors to go in the same direction so the robot will move forwards. So the forwards direction for the motor 01 and 01. So if I want the robot to spin on the spot, so command code 5 for example, I need one motor to go forwards and one motor to go backwards to make the robot rotate. Again, we're starting off with a simple example with this robot controller architecture. But this is exactly the same process that you'll go through when you design the instruction decoder inside our processor. Now there's a number of different ways you could design this command logic. You could just use classical Boolean algebra to do that, so from your truth table, or we can design it using a decoder, encoder architecture, or one based on multiplexers. So we look through both of these towards the end of this lab here. So can you implement the control logic, the decoder, to produce the required control signals either based on our multiplexer or by using an encoder-decoder circuit. Again, to test to see if your answers are right or wrong, you can use the VLE to auto-mark your answers. You'll find that in the same section as you downloaded this exercise sheet. Okay, I think that's where I'll wrap it up. I'll see you in the next lecture.